All right, well, here we have the beginning of a brand new paradigm. So let's do a little paradigm shift. I think you're going to like this one. I should show you the testimonial from one of your former students in this class who he hated Prolog, and then he went to graduate school, and then he got involved in this big project, and he has grown to love it. I'll have to show that to you sometime. All right, so here's our new paradigm. It's the concurrent paradigm. So here's the first question that we want to ask is, what is concurrent programming? In fact, that's going to occupy the first section of this lecture. Exactly what is concurrent programming? Okay, so in English, what does the word, if you do two things concurrently, what are you doing? You're doing them at the same time. So I venture to guess that every program that you have written so far in your computing career, when you write a program in your mind, how does it execute? You write like one program at a time, and when you run it, how does it execute? Just from start to finish, right? And it's the one program. Are you with me? So now what we're going to look at is the situation where instead of having one program run from start to finish and a second program running from start to finish, what we're going to have is we're going to have two programs that are running at the same time, and furthermore, they communicate with each other before they end. Are you with me? So more than one program executing at the same time. That's basically what concurrent programming is. Now, it turns out to be this particular paradigm. In this course, we are devoting a disproportionate amount of weeks to the concurrent paradigm because it is getting more and more important with the passing of every single year. So how many, do you guys know, like how many processors, do you know the word core? So do you know how many cores your laptop has? Oh, yours has 4. I think I have an old one that has 2. How many cores, you know, how many? So what a core is a separate processor, and this is the trend in hardware now, is to have multi-core processors. So what a multi-core processor is it's in essence, it's more than one central processing unit, and these things are executing at the same time. And it used to be that all laptops only had just one processor in them. But it's a recent trend that in order to get performance, the hardware engineers are putting multiple cores on a single chip.
Mm-hmm. With those really old-fashioned, huge computers that would take up a whole room?
Yes.
How many cores would they have?
No. Those big old huge ones that took up rooms, one. It was one from the beginning. At the beginning, it was always just one processor. Even those big ones that took up whole rooms. The advent of concurrent processing evolved, and it wasn't that way at the beginning. Yeah. And what happened was, but it's interesting because, like in my lifetime, what happened was the way they would make the computer faster is they would take that single central processing unit and they would speed up the clock rate, so more cycles per second. And they kept doing that over and over and over again until pretty soon they kind of like hit a brick wall. They couldn't get them to go much faster because of the hardware technology involved. But on the other hand, they were able to miniaturize the circuitry, and so they were able to put more circuitry on the same chip, but it didn't help that they could put more circuitry on, because if they put the more circuitry on and they used that circuitry to speed up a single processor, it wasn't speeding up very much anymore. It was like 1 or 2%, 5%, whatever. So to get really more performance, they scaled back doing it that way, and when they added the circuitry, they'd actually add a separate whole processor on the same chip. Are you with me? So that's what concurrent programming is. So, we're going to be using this book. Actually, there's going to be 2 books for this section. There's this book by Ben-Ari, Principles of Concurrent and Distributed Programming, second edition. I hope you guys all have this book. We're going to start with it. And that's kind of like the theory and the practice. We're going to do some programming in Java and another language called C++. But here, I recommend, if you're ever going to do any serious programming in Java, I recommend you buy this book and keep it. This, Java Precisely by Peter Sestoft, it's in its second edition now. This is the numero uno best reference to Java. And we're going to use a couple of the examples in here in detail we're going to look at. And so this is a good one like to have if you know that you're going to be programming in Java. It's a good one to have on your shelf to refer to. Mm-hmm.
So we're going to be using those two books concurrently?
Yes, we're going to be using those two books concurrently. We're going to be reading them at the same time. Yuck, yuck. Okay, so let's talk. Let's see exactly how this concurrency works. First of all, we have to understand the time frame. Here's a slide 1.1 from, and these slides are from the Binari book, Principles of Concurrent and Distributed Programming. And here again, all these slides are on the webpage. So, and we see here that time is measured in terms of nanoseconds. Now, how long is a nanosecond? 10 to the what? Do we know this yet? Is it not 10 to the 9 or 10 to the minus 9? Yeah. So what is let's review these. What is a millisecond? 10 to the minus 3, which is a thousandth. What is a microsecond? 10 to the minus 6, which is not a thousandth, but a what? A millionth. And what is a nanosecond? 10 to the minus 9th, which is a billionth. So we're talking about times in the nanosecond region when we talk about the cycles of the CPU. And then we can compare this with human time, and of course in human time we're talking about things that we are not upset when our program doesn't respond within 100 nanoseconds. But we are upset if it doesn't respond within 100 seconds. Are you with me? So there's this big disparity between human time and computer time. And what happens is in the history of computing, it's very interesting. Because the computers could execute so fast in the early days with primitive operating systems, when humans were programming one job at a time and they were putting it on the computer, and most of the time the computer would be idle while you would submit a job. So a single user would submit a job at the computer center, and then the operator would go and he would take your job and he'd put it in, and then that whole computer would be dedicated to running your job and your job only. It was like be one job at a time. Then after you get the results of that job, then he'd take that out and he'd put the other guy's job in. And then that computer would run the other guy's job. And it would just be, one right after the other. Okay? So this next figure, this is a figure from the book that we're going to use next, the book that I wrote that we're going to use next semester, Computer Systems. This is from chapter 8. And this is a primitive this illustrates a primitive one job at a time system. So you see what happens is, and that this illustrates the scenario that I just described. Do one job at a time. Well, what happened was, as time went on, people realized that, gee, most of the time the computer's sitting idle because it can do all these cycles per second, and we're sitting waiting there for somebody else's job on a human time scale, to get set up. And we're wasting all of this processing power. So what happened then is, operating systems evolved, and with operating systems came this big advance called multiprogramming. Now, with multiprogramming, and here again, this was the early days before we had multi-core was common. And with multiprogramming, what happened was you only have one processor. Okay? So like an old laptop would only have like one core, one CPU with just one core. All right? But what would happen is the operating system would manage more than one job at a time. But it really wasn't executing more than one stream of instructions at a time. All it was doing was switching rapidly between one job and another job. Okay? So here is the definition of multiprogramming. An operating system that can switch back and forth between processes to keep the CPU busy is called a multiprogramming system. Are you with me? So, and just imagine your own laptop, and if it has one core, you could be doing things like playing your music and writing on a word processor with Microsoft Word or whatever, okay, at the same time. Now you think you're doing that at the same time, but really what's happening if you only have just one processor? Really what's happening? In a few hundred nanoseconds, it's doing your music, and then it's going and getting the keyboard input, and then it's doing the word processing, and then it's going back to the music, and it's doing this, and it's doing this. And does everybody see what it's doing? It actually has to switch back and switch between these jobs. So I think it helps to have a little, what we're going to do now is we're going to try to get a mental picture of how the mechanics behind how that works, how the operating system does that. Do you have a question? Yeah?
Is that why like on old computers, if you open it up too much at once, like one would start freezing?
Freezing it, yeah. All that is operating system technology that couldn't handle that, right. So, yeah. And the processors weren't very powerful, and so you'd have more than one job, and then they'd get all stacked up, and it couldn't handle all that stuff, and then it would slow down. Yeah. But the way that it actually does that is the way that the operating system maintains this illusion that things are happening at the same time, even though they're really not, is it maintains a queue of process control blocks, PCBs. So that's an important phrase for you to understand, for you to remember. A PCB is a process control block. And I think it'll help to have us have a mental model, a mental image of what a process control block is. Now, so let's think about this for a minute. First of all, how does the operating system know whether to switch from one job to another job? I mean, like if we had that scenario where there's like a word processor and a music player, and you know it needs to process the keyboard input. How does it know when to stop doing part of one job and start doing another part of another job? Well, what happens is inside the hardware of the computer, there is like an alarm clock. And the operating system can set the alarm clock to go off at a certain number of nanoseconds into the future. Do you see what I mean? And then what it can do is it can take the next job that needs to be processed, put it in there, turn control of the whole processor over to the job, to the application, and that app can be running, and then all of a sudden that hardware alarm clock goes off. Bzzz. And what that causes is what's called an asynchronous interrupt. So here we have two different examples of asynchronous interrupts. The first one is the timeout, which is the one I just described. Okay? And so when that alarm clock goes off, the operating system then takes over. The hardware has a way to allow the operating system to terminate that executing job and put it aside, and then put the next job in there and turn the CPU on over to it. Do you see how that, I mean, just conceptually, see how that works? Now here, so that's one reason that a job can be interrupted, but here's another one, I/O completions. I/O stands for input-output. So suppose that you have a program, suppose that you're starting up Microsoft Word and you want to open a new document. Where does that document reside? On your hard drive. Okay? So now, the thing about a hard drive is, it's really slow compared to the CPU speed, right? So, if the operating system, if your program wants something off the hard drive, why should the operating system wait for the hard drive to spin around and get that before it continues. It would be better if it did what? Switched you out while the hard drive was getting its information and worked on another job. So that's another way an asynchronous interrupt can happen, is with an input-output completion. So that's an example of a. And then what would happen is, after the data was read from the hard drive, then the operating system would say, oh, okay, now you're ready to run again. Okay? And the operating system has to manage all that. And so those are examples of asynchronous interrupts. So now here is a timeline that is not just one job at a time, but this is multiprocessing. Now what did we say multiprocessing was? Many processes, but with one what? Processor, with just one processor. Are you with me? So one processor, many, and it's actually switching between them. So here's an example of a multiprocessing of what it would look like. So here's job 1. So here, in this scenario, the operating system sets the timer. It turns control over to job 1. The alarm clock goes off. Bzz, oop, you're out. Job J2, and it sets the alarm clock for him. Bzz, timeout. Oh, okay, we're putting in job 3. Job 3. Bzz, timeout. Oh, we'll go back to job 1. So now here's job 1, but now all of a sudden job 1 did what? Maybe requested some information from a disk. So now, requested information from a disk. We'll put you out, and we'll put job 3 in here, and then maybe he'll time out. But then maybe then after job 3 times out, then here's job 2. But now maybe job 2 asks for something from the disk, from the hard drive. And so and so you see how it goes like this. And so it's all these things of. Now I ask you, can the programmer predict when her program is going to be interrupted in a system like this with all of these Microsoft Words and all these applications? Can you predict where exactly in your program it's going to be interrupted? Impossible. You don't know. Are you with me? It's impossible to predict that. It's too complicated. I mean, how do you know how busy, what other jobs are going to be in the system? And these timers, you don't know when it's going to time out. So here's the thing. Your job can be interrupted at any specific time, and you don't know ahead of time where it's going to be interrupted so that another job can do its thing. Now, that's a key concept. Is everybody with me on that? So there is some, so we can't predict when those timeouts are going to occur. So that's our big observation. It is impossible for the programmer to predict the statements in the program where the process will be interrupted by the operating system. So that's a key idea in concurrency. Yeah? We don't know. Who knows? And maybe your program would work if it gets interrupted in one little place, but maybe it won't if it gets interrupted in another little place. And if you test it and it didn't get interrupted in that one little place, that would cause the bug to appear. You might think it's correct because it tested right, but maybe there's a bug in there anyway. You see how hard it would be to test, a concurrent program. Yeah, did you have a question?
I'm failing to see the concurrency.
That is a very good point. The question was, I'm failing to see the concurrency. In fact, you are right. This isn't real concurrency. What is it? It's apparent concurrency because of those different time scales that we have. And in human times, it seems like they're running at the same time, but in the reality, it's not. So that was an excellent observation. At this, with what is this? What did we call this? Multi what? Did we just call it multiprocessing or multiprogramming?
Multiprogramming.
Boo! Oh, maybe I said it wrong.
No, it's multiprogramming.
Oh, you know what? My slide is incorrect here. Oh, bummer. This is really a bummer. I'm going to have to change this and repost it. This slide should not say a multiprocessing system. It should say a multi-what? Programming. Oh, and and I read that, and it was wrong. Yeah, it's multiprogramming. So
The one before said programming.
Yeah.
Good. I'm glad that, Yeah, yeah, this one's right, yeah. Yeah, I need to change my slide there. This is a yeah, in fact, we're going to make a distinction between multiprogramming and multiprocessing, and I just wrote the wrong one up there. So you are, but anyway, your observation is still an excellent one. The concurrency is only apparent in multiprogramming. Are you with me? Because it's this fast switching in between. Okay? So now, some more terminology. First of all, we are going to talk about the word process. So here's the definition of process. A process is a program during execution. Are you with me? It's a program during execution. Now, why is that an important concept? Because when you have these jobs that are in the operating system and they keep getting scheduled one after the other, partially completed, and each one of them is partially completed, what happens is the operating system has to save that process when it gets interrupted so that it can do what? Take up right where it left off, and the programmer is none the wiser. Do you see what I mean? Is everybody with me on that? So I ask you a question. How in the world is the operating system going to save all the information necessary to start it up right from where it left off? What is it going to need to save? Suppose you have a program just written in C++, boom, 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 and I tell you, suppose you're in the middle of a loop or something, and I say, oh, I'm going to cut you off when you execute this statement. I'm just going to cut you off. Well, you're going to have to save something somewhere, but my question is, what is it that you're going to have to save in order to go back and start tracing that program again right from where you left off? What are you going to have? Do you see the question?
Values, registers.
You're going to have the values of all the variables in your program. Yeah. And not only that, you're going to have an indication of what? Of which instruction to do what? To execute next. Are you with me? Does everybody see that? And do you remember in formal methods when we talked about state? Do you remember what the definition of state was? List the variables and all their what? And all their values. That was the state of the computation. So what has to happen is that's what the process control block stores. It stores the state, the values of all the registers and the values, of all the values in the register. So that whenever, and furthermore, a pointer, it's called the program counter, of which instruction is going to be executed next, right? So the state of the process is specified by the program listing, the values of all the variables, and the next instruction to execute, so that you can start up at that point with those values, and it will appear as if nothing happened, as if it never got interrupted. Is everybody clear on that? So here's actually a picture of it. The operating system stores it in a queue. And each one of these is a PCB, process control block. Yeah? And what it does is each one has an ID. So have you guys do you run your activity monitor? Do you know how to do that? And have you noticed that there's an integer that identifies each one? It's the ID, process ID. The operating system, numbers each one, keeps a list of them. Okay? And then another thing that stores is how much CPU time has been allocated to this process, so it knows who's been in there a long time and who hasn't, which process has been in there a long time. And then this PC is the program counter, so that points to the instruction that's going to execute next when you resume it. And what is this SP? What do you suppose the SP is, for those of you who've had computer systems? Or that's the stack pointer. So because when you're running, you got the runtime stack going up and down, right? You got to know, where's my runtime stack if you're going to start up from where you left off. So all that stuff gets stored, and it gets stored in a process control block like this, in a queue like this.
So process one stuff would just stay on the stack when it gets switched off.
Yeah, each each individual process has its own little stack in memory, and it stays there. And then when you start up, but the stack pointer in the CPU has to go back and point to where that top of that stack is when you go to start up again.
Oh, so that stack, process 1 stack is going to be at a completely different location in memory than process 2 stack?
Yes. Oh, absolutely. Oh, no. They do not share runtime stacks. Each process has its own runtime stack. Yes, that's definitely the case. Right? So that it can, because otherwise everything get all garbaged up, you know? So, right. Is everybody, but that's a good question. Is everybody with me on that? Now this next figure, figure 8.19 from this book, is, it's really important that we understand, this is a classic picture of what happens to a job in a multi-programming system. So let's imagine that the job is Microsoft Word, and you want to start Microsoft Word. So when you click on the Microsoft Word button, you know, the icon thing that starts it up, what that does is that causes the operating system to create the process for that application. Are you with me? So it creates the process for it, allocates storage for the stack, it does all the bookkeeping that it needs to do, and it sets it up, and at that point, and then it puts it in a queue of processes. And that queue is called the ready queue. Now, so when you see this ready corresponds to a queue of processes, of process control blocks, right? Is everybody with me on that? So there's a queue here, and it's in the ready queue. Now, if there's only one processor, what happens then is the operating system selects from the ready queue the next process to get some CPU cycles to execute. Yeah? Are you with me? And once Microsoft Word gets selected, then it makes a transition. When it's selected to run, now it is actually physically running in the CPU. So the CPU is doing fetch, decode, increment, execute, repeat. Remember that from systems? That's the von Neumann cycle, right? So here it's running. Now suppose that little alarm clock goes off. Then the operating system takes it out, and it saves all those registers and puts them in the what? In the ready queue. And then maybe later the operating system will select it again, and then it's running, and if an IO request happens, then there's a separate queue of process control blocks waiting for input-output. Are you with me? And then once the disk gets the information and it's ready to run again, then the operating system transfers the process control block from the waiting queue to the ready queue. Does everybody see a mental picture of how that happens? And then it will keep going here. It'll keep looping around here. Sometimes it'll be selected to run, sometimes it'll time out, sometimes it'll be waiting, sometimes it'll be ready, sometimes it'll be running. And finally, whenever you do quit, when you quit the app, then what happens is the operating system terminates the process, and all those resources go away, and it has now died and it's out of the system. Now, does everybody see the picture of how that works? Yeah.
Is getting the disk to give you the information in the process yourself?
Actually, these days it is. In the early days, it wasn't. But these days, each disk, that's called a controller. These days, each disk has its own disk controller that is actually running concurrently.
Okay.
But that's a detail that we don't want to get into. In the early days, that was the same processor had to do one processor had to do the whole thing. In the very early days. Now, let's go back, now that we made that correction, let's contrast that with multiprocessing. So what does this slide say is the definition of multiprocessing? It's a computer system with more than one what? Physical CPU. CPU is a central processing unit. Yeah? With more than one physical processor. So now what happens is, the operating system still maintains a queue of process control blocks, but what happens is, because there's more than one processor, more than one of them can literally be running at the same time. That's the difference between multiprocessing and multiprogramming. Are you with me? So here's a little figure of a block diagram. Now those of you who have had the computer systems course should recognize this. You know, you got the bus here, you got the input device, you got the output device, you got main memory, okay? And here's an example of more than one CPU in the system. Physically, more than one physical CPU. And when you talk about cores, that's what a core is. A core is a separate little CPU. And now here comes a really, really important concept. This is called the concurrency theorem, and unfortunately this theorem is not explained in our book, but this is a really important one just to distinguish between these two. The concurrency theorem says this: multiprogramming and multiprocessing are logically equivalent. Multiprogramming and multiprocessing are logically equivalent. What that means is that it doesn't really matter if you have one processor and you're switching back and forth between two programs that are communicating. It doesn't really matter if it's doing that or if it's doing what? Each one has its own what? Processor, you know? Because in both situations, what are they having to do? In both situations, what are they having to do? They're having to communicate with each other. You see what I mean? It's just that in one case, they're actually doing it literally at the same time. I mean, they're executing literally at the same time. In the other case, they're switching back and forth. But the same problem, we have the same issues, we have the same concurrency issues, regardless of what physically is going on. Whether it's switching back and forth between two of them with one processor really, really fast, or if you have two separate processors. In both cases, they have to communicate with each other, and they communicate with each other basically the same way. You see what I mean? So multiprogramming and multiprocessing are logically equivalent. So you can think of it either way. And in fact, what we're going to do now, what we're going to do this is the end of the first chapter. Now what we're going to do in the second chapter is we're going to see how we have to think about this concurrency paradigm. And the main thing is, we have to understand is that these things, whether they are literally happening at the same time or whether it's switching back and forth, what's happening is they're being interrupted. And things are happening in between, you know. You see what you see, that's the idea. Okay, so let's go to the second chapter. And the title of our second chapter is The Concurrent Programming Abstraction. Now, I have a little, this might be showing my Americanism. In the United States, we mostly, in the hardware, we call it a program counter. Those of you who took the computer systems course, you know what the program counter was. That was a register in the CPU that pointed to the instruction that's going to execute next. Well, that's really common terminology. I prefer to call it the program counter. And when you read the book, he calls it a control pointer. But it's hard for me to break this habit. We're going to still call it the program counter, okay? So if you don't mind. That's a slight difference in terminology. Okay. So now, here is an example of three processes. And we're going to call them P, Q, and R. Process P, process Q, and process R. And what this listing illustrates is you can imagine that process P is executing a program, and in the program listing, P1 is the first instruction, and P2 is the second instruction, and P3 is the third instruction, and so on and so on and so on. Are you with me? So in your listing, it's like first there's P1, then there's P2, then there's P3. And also in process Q, it has some instructions in its program listing, and they're labeled Q1, Q2, and Q3, and the same way with process R. But the point of it is that each process has its own program counter. So each one of them has a pointer to the instruction that's going to be executed next. Are you with me? Is everybody clear? And then what we have to imagine, well, here's an example with two processes and each with two statements. So process P has statement P1 and P2, and process Q has statement Q1 and Q2. So now here is the situation with concurrency, you guys, and this comes a different way of thinking now. We don't know where these things are going to get interrupted. Let's suppose that we're in a multi-programming environment where there's only one process, one processor, but two processes. Can you give me a scenario for how these statements could execute? In what order these individual statements could execute? What could happen? I mean, what's one possible scenario? What's one real simple scenario is that process P1 just executes from start to finish. So that would be P1 and then P2, and then process Q could execute from start to finish. So that would be Q1, Q2. So then the sequence would be P1, P2, Q1, Q2. But we can't predict. It could be what? It could be that what happens? It could be at P1 and then it gets interrupted. And then what? Q1, then it could be like maybe Q2 if it didn't get interrupted, and then it could go back to P1, to P2. Are you with me? So tell me, what are the possible scenarios? This is called a scenario. What are the possible scenarios that we would have with two processes with two executing statements? Whereas you know in the listing though it's P1, P2. I mean, P1 has to execute before P2, but you don't know what the interleaving is going to be. Can you tell me how many different interleavings there's going to be? Could you figure that out? Well, I mean, what's the particular number for these? 4. You think so? So Nate, can you list them off? P2, Q1, Q2.
Process P always executes first.
No, not necessarily.
So it could be 6.
Oh, so now maybe you're thinking 6. Actually, it is 6. Here they all are. Slide 2.2 in our book. Yeah, see, you left out the, okay? But anyway, but look, it could be P1, Q1, P2, Q2, or P1, Q1, Q2, P2, or P1, P2, Q1, Q2. Now, in all of these, you see that you have to consider all those possible interleavings. Are you with me? To predict what's going to happen at the end when they're both done. But the one restriction that you have to have in these interleavings is that P1 has to happen before P2 and Q1 has to happen before Q2. Are you with me? When you enumerate them all. Is everybody clear on that? Okay. So now, let's take a look at how our author displays concurrent algorithms. So first is algorithm 2.1. Again, this is from the book. It's a figure from the book. And here's algorithm 2.1. It's called a trivial concurrent program. And it's just to illustrate the format of how we display concurrent programs. So notice what we have here is, first of all, we have the name of the algorithm, and then up here in the second little compartment, we have a global variable. Now this global variable is shared, right, between this program and this program. So both of these programs have access to integer n, and what do you suppose this left arrow is? Yeah, that's it, right. Correct. It's the assignment statement, gets. So we have this integer, n gets 0. So n is initialized to 0 at the beginning. Are you with me? And it's global. And each one of these has access to this. But now, inside this p, we have an integer k1. So what do you suppose k1 is? It's not a global variable, it's a what? It's a local variable, so it's local to p. So if you're over here in q, q does not have access to k1. Sorry. Q does not have access to K1. And similarly, K2 is a local variable in process Q, and P does not have access to integer K2. Are you with me? And so in the beginning, what is the state of the process at the beginning? The state is N has the value 0, K1 has the value 1, and K2 has the value 2. And here is an here's an assignment statement. P1, N gets K1. Here's an assignment statement. Q1, N gets K2. Here's my question for you. What is the value of N after these two things run concurrently? It depends on the interleaving, doesn't it? Yeah. And so what are the two scenarios? If what happens? If which is N would have the value of what? Well, but K1 was initialized to 1, so what would the final value? Whereas on the other hand, yeah, so does everybody understand that if we run this two concurrently, we cannot predict exactly what the output, or what the final value of N would be? Because you don't know what the interleaving is.
Why would you ever use global variables with multiprocessing or multiprocessing?
That is a really good question. The question is, why would you ever use the global variables? Because that is by far the most common way for concurrent programs to communicate. If they don't have anything in common, there's no concurrency issues. You see, if they're just all isolated and they don't, then you're not really doing concurrent processing. You're just processing one job and you're processing another job. But see, that might be, that common data might be a big array of data, and you might be trying to use more than one processor to do some matrix manipulation on that data. And you want to have more than one process doing that at the same time. So you share them, so they share that data. That was a really good question. So that is how these two processes communicate. It's by sharing data. That's a very common, and that's probably one of the most common. Now, some people say you shouldn't do it concurrent processing this way, and there are different approaches, but that's a common way, and we're going to use that. We're going to use that technique for communicating between concurrent processes. You see what I mean? So yeah, very good question. Is everybody with me on this? Okay. So actually, we've already done with this. Algorithm 2.1. N is a global variable. K1 and K2 are local variables. What are the possible final values of N? You told me what they were. And we can analyze this now with a state transition diagram. Now, our author is going to take a little detour here to show what a state transition diagram is. Here's a trivial sequential program. So this is not concurrency. Here we have integer n initialized to 0, and we have K1 initialized to 1 and K2 initialized to 2. And we have, this is a statement P1, and it's n gets K1, and then statement P2 is n gets K2. And the only reason we have this trivial thing, this trivial little program with only has two statements in it, some initializations and two statements in it, is to show what a state transition diagram looks like. Now check this out, you guys. We're going to do state transition diagrams, and we need to understand how they work. But those of you who are in computer systems know what state transition diagrams are, right? So look, what does this initial node here have in it, in this state transition diagram? What is the state? The state is K1 equals 1, K2 equals 2, and N equals 0. Are you with me? And then up here is the statement that's going to execute next. Does everybody see how that works? So here, this is the statement that's going to execute next. Are you with me? So now, if this statement executes, what happens? N gets what? K1, which is 1. So when that statement executes, that changes the state from n equals 0 to n equals 1 over here, And now what do we have? So K1 is still 1, K2 is still 2, N has been changed to 1, and now the statement to be executed next is this one. And then when that one executes, we're at the end, and N has the value 2. So this is the start state, and this is the final state of the computation. Are you with me? Now, on the other hand, what does a state transition diagram look like for a concurrent program? We don't know. So let's go. Do you remember that our original concurrent one that we saw? There, P1, so look, P1 is N gets K1, Q1 is N gets K2. So now we have more than one. We don't know which one of those is going to execute next. Do you see what I mean? And we start off with the state K1 is 1, K2 is 2, and N is 0. If, in fact, P1 executes first, what will it do? N will get what? K1, which is what? 1. So do you see over here, N is 1. And now that we don't have any choice now for the next one, right? And so now if when Q1 executes and N gets K2, then N gets 2, so we end up with the value of N of 2 down here, and we're at the end. On the other hand, if Q1 executes first, then we branch to here, and then we end up here. And these are the two things that you told me. You told me that the final value had to either be 1 or 2. So this is just a picture of what that looks like, what that scenario looks like. Now, check this out, you guys. This is a great puzzle. This is a great puzzle. For your homework for Monday, now you have this concept of how these things can be interleaved, right? Watch this. There is an algorithm that our author gives. It's 2.9, and let's take a look at 2.9. What you have to do is you have to determine an interleaving so that this concurrent program will terminate with a value of 10 for N. Now watch this. Here's algorithm 2.9. This is a counting algorithm, and look at here. Here, we start off with a global variable, a shared variable, so they both have access to N, and it's initialized to 0. And here we have one process, and here we have another process. So here's process P, and we have a little local variable here called temp. Are you with me? And it's an integer. And now, what is this P1? It says do 10 times. So you know this is like a 4. This is like 4, I get 0, I less than 10, I plus plus. Yeah? But without the I. We do it 10. Are you with me? We do it 10 times. And so what does it do? It does temp gets N. So if N is 0, what would happen? Temp would get 0, and then what? N would get 1, right? And then if it executed again, what would happen? Temp would get 1, and then N would get 2. And then it would do it again, and temp would get 1. Sorry, temp would get 2, and then N would get 3. And if it does this 10 times, what would happen? What would the final value of N be after this loops 10 times? If this just loops 10 times at first, what would the value of it be? It would be 10. And then if this one starts up, what would it do? Because remember, this N got changed over here. So then after this loop 10 times, if this one starts up, what will it do? Temp gets N, N gets 10 plus 1. So then that would make N what? 11, and then what? 12, and then 13, 14, 15, 16. And so the final value would be what? 20. Now does everybody see that if you ran this to completion first, it would make it 10, and you run this to completion, it would make it 20. On the other hand, if you run the Q to completion first, and then this one, it would still be what? Now if you run Q all the way to completion 10 times, that would ratchet it up to what? To 10, and then this one would take it up to what? To 20. But what's your problem? To find out of what? An interleaving, so that, check this out, so that even with this one going 10 times and this one going 10 times, the final value of N is only 10 and not 20. it actually doesn't matter because P1 doesn't do anything anyway to N. So the question was, does P1 actually execute? The answer is, yeah, it does execute because it has to do that test. You see what I'm saying? It does have to do that test, but it could be interrupted. You understand? It could, instead of, if the first one runs to completion first, the sequence would be P1, P2, P3, P1, P2, P3, P1, P2, P3, but, and then after that, it would be Q1, Q2, Q1, Q2, Q3, Q1, Q2, Q3, Q1, Q2. Boy, see that 10 times fast. But it could be what? P1, P2, P3, and then Q1, Q2, Q3. I mean, you know. So can you figure out a way, can you figure out an interleaving? This is what you, this is the paradigm shift. This is the paradigm shift. It's when these things are running concurrently, you have to imagine that they can be interrupted with arbitrary interleavings that you have no way of predicting when that interleaving is going to happen. Yeah? And it's a different way, it's a different way of thinking. All right, you think you can do that? You should be able to think it through and how the assignments work and figure that out. Okay, good deal. See you on Monday. Have a great weekend.